All right, good morning, everybody.
Morning.
Good morning.
Morning.
Hope everybody had a good weekend. So I just moved this weekend. Well, I'm in the process of moving, but at a new location, so you have a new background and good stuff like that. And new technology, so we will see how network connectivity works here. I'm wireless instead of wired, so hopefully the bandwidth holds, but we'll see and we'll adapt. All right, let's start off with any questions on PA2, the stick playing game.
I had one, but I gotta remember it.
Okay. And I posted an announcement that there's a sample executable on the Linux server that you can play with. So if you do /temp/stick, that'll run you through the game. And this should your code should mimic this, right? Where you can put command line arguments, or you can put in an argument when you're running. And if you make any mistakes, it just gives up right away, whether you did it on the command line or you typed something when it asked you how many sticks. And if you play correctly, then you can put in bad information as many times as it takes to answer, 1, 2, or 3, and just play the game as usual. And most of PA1 applies to this, except for the change in how you start the game. The fact that the computer always goes first, and the fact that you can make an infinite number of mistakes while specifying the number of sticks. All right, go for it.
So basically the way that I do the validation for error handling, when you input a number into the command line, if you give it a 0, it will ask you to how many sticks do you want to start with instead of erroring out.
Okay, is there a reason that you're doing it like that?
Basically, I initialize the variable to 0, and then I just check if it's 0 to basically ask how many it wants to take, or to decide on whether it's going to ask you.
Okay, are you not using scanf?
I am.
Okay, so instead of initializing the variable and seeing if it changes, how about checking the return value from scanf and use that to tell whether they typed in a valid number? Because if they don't type in, if they type something on the command line and it's not precisely a legal integer, at least 20, you want to exit the game after an error message.
Yeah, it'll do all that. Everything else will always do.
But if they do this, you wanna print an error message and exit.
Okay.
Do you have any objections to me using an if that elif else and endif for making a thing work on both Linux and Windows, because I'm using a clear console command. It's different on different command lines.
I'm okay with that. Yeah, as long as they will compile and run on linux.engrcs.com and compile with just a plain old, gcc-o stick.c. As long as I can do that, build an executable and run it, I'm okay if you put in those extra features, that's fine. Alright, go ahead and send me an attendance note, let me know you're here. And don't forget the dash here part. Sure.
might be a misnomer here.
That's
I
why
was
we're here.
I was told that structs are usually something that's passed by value.
Well, so that's a longer conversation. The short answer is in C, everything is passed by value. Even when you're passing an address, you're passing the address by value. But that's a theoretical answer that's not terribly useful. Usually when you make a struct, so we'll talk about structs a lot more in winter term, but you know in C you can do something like struct. You know, I can define a point, and it contains a pair of things, an integer x and an integer y. And then you've got basically a new type of variable at your disposal. I can say struct point p1. And if you want to pass this to a function, we're going to talk about functions today too. If you want to pass that to a function, you can just pass p1 as an argument, and it will pass basically the value of this structure, including these things. But probably the most common thing we would end up doing is make this a pointer to a struct, and then allocate space for it. And then when we pass it to a function, we would just, you know, call function p1. But in our function, we would declare the argument to be a pointer. Like that. So I'd say probably we typically, as C programmers, we end up passing an address of a struct point more than just the structure itself. But you can pass the structure, it'll actually do it.
I've been using like pointers in my pointers to structs in my PA2 program.
Okay, cool. Is that working out?
What did you need a struct for?
I used it as a game state. Is the game over? Has the player won? How many sticks are there left? It's all in a struct.
Cool. Yeah, one of the nice things about structs is that it lets you take, you know, lots of different pieces of information and combine them, and then you just have this one thing. And if you've got, you know, a function for printing the game state, a function for making a computer movie, you just pass this one thing to it, and you've got all that information. Now, if you just write, you know, one big long program with no functions, everything's effectively global. But yeah, structs are a nice way to clean that up. I got some weird shadows here. Let me try this. I got weirder shadows. If that doesn't help. All right. Other questions or comments?
Yeah, about ODP 410. Are you wanting us to name it pick, or do you want us to name it ODP 410?
Your function needs to be named pick.
Okay.
So we'll go
Okay.
we'll go through the ODP in a few minutes too. But yeah, so this starts a different version of ODP where you're going to basically write a function and then link it to what I call a test bed, which is a program that will use your function, and then you basically assess that test bed. But we're going to run through that in detail in a few minutes. But before we get to that, let me mention there's an online quiz that's coming up due Wednesday morning at 8. And you could have done this at any time, but particularly since we've talked about fgets and scanf, this is a good time to do it. But it's basically 4 questions, and it's just asking you to type in some code and then answer, you know, a question about what it does. So type this program in, and it will do one of these 4 things. And then type this program, and it'll do one of these 4 things. But my suggestion is don't just, you know, blindly do this. Think about what it's doing, right? The idea here is that we're using scanf, which I said not to use, right? So here's some code that uses a scanf. And then here's some code that uses scanf in a loop. And then here's some code that uses fgets and scanf, which we've said is the way that we want to process input, do the ingest and parsing of data from the user. So make sure you do that before 8 a.m. Wednesday morning. And let me know if you have questions about it. All right, so yeah, let's look at the ODP. So your goal here is to write a function named pick. Okay, so we'll talk about functions too in general in a few minutes, but let me go through this first, and then we'll review functions in C. So you're going to write a function named pick. It's a function you're creating, and it takes one argument, which is an integer, and it returns one value, which is an integer. So the prototype for the function would be something like this. Remember, when you make a function in C, you have to prototype it. You have to describe to the compiler what the function will look like, even before you actually go ahead and write the function itself. And so a lot of times when you're asked to write a function, you're told what the prototype will be. And when you write the function, you're not going to say integer pick parentheses integer semicolon. You're going to say something like integer pick parentheses integer n, and then go into a curly bracket. And if you just wrote integer pick parentheses n semicolon, that's not how you actually write the body of the function, right? It's how you do a prototype. So we'll do some examples of this. So what does your pick function do? It takes an integer, and if we call that argument n, you can call it whatever you want, but for the sake of discussion, if we call that n, it should return one of two things. If n is not a multiple of 4, return n modulo 4, n% 4. If it is a multiple of 4, return 1. This should sound familiar to you, right? This is your algorithm for how a computer, given n sticks left in the pile, decides how many sticks it's going to take. And it's going to be either n mod 4, or if there's exactly a multiple of 4 sticks left, it'll take 1. So this is something you can use in PA2 as part of the code for how the computer makes a move. Alright, so here's how these ODPs work, right? You're going to write this function. So you're going to make a file pick.c, and inside there you're going to put this code for your pick function. And that is not an executable program. That's not something you can compile and run. It's just a function. It's not a main program. So if you want to test this, you have to make your own main program. And you can do that however you want. And there's easy ways, and there's more difficult ways, and there's really complex ways. And a lot of times the more complex ways do a better job of testing your function. But we can do some pretty simple tests also, without having to do a whole lot of work. Okay, so you're going to do that. You're going to test your pick program until you're pretty sure, hey, my function works perfectly, right? And then you're going to go ahead and assess it. And so to assess it, you're always going to do something like this. So this says, let's compile my pick function, which is in pick.c, and let's link that to the pre-compiled test bed, which for this assignment is /temp/odp410main.o. So we're going to compile those together. We're going to make an output file called pick. And then when you're done, you're going to use the assess command. And assess will take 2 arguments as usual. The name of the executable image that you built, pick, and the name of the source file, pick.c. And once you do this, you can't really run pick by yourself, right? Pick is designed to work with the assessment system. If you just say pick, it may give you a seg fault. That's okay, right? What you're supposed to do with pick is run it through the assess command. But if you want to test your pick function first, right, do a gcc-o pick.c in the name of your test main program.
Question.
Yeah.
Do you need the include stdio at the top?
If you're doing any input-output or using anything from Standardio, then you would need to include that. You probably don't need that for this because pick does not produce any output, it does not read any input. It's just a function that takes an integer and returns an integer. But if you put in, debug statements while you're developing this and you want to do prints and stuff, then you'd need Standardio.H. And it generally doesn't hurt you to put that in. If it's already been included somewhere else, it'll usually not do any harm. But if you need it and you don't put it in, you'll get compiler warnings, and that'll tell you. All right, so let's do some examples. So, let's start with a pick.c, and I won't write a working pick.c, but it's not that many lines of code to make this a workable program. But let's just explore it. So let me go into my home directory. Do I have a 224 area? Yes. All right. So I'm going to write my pick.c. And I don't know, I didn't read the assignment very carefully, so I'm just returning n. All right. So there's my program, and I'm super optimistic. I think this is going to work, right? Because I paid attention in class. So I'm just going to go ahead and assess it. So gcc-o pick.c/temp/odp410 main.o assess pick.c, and I'll say go ahead and grade, and I got 0 out of 10. So I didn't read the assignment very carefully. All right. So if I just try to run pick from here, I don't know what it's doing. It's just kind of sitting here, and I can hit an enter and it prints out a pattern, and so I can't use this function that I built by doing this compilation. I can't really use that to tell what's going on with my pick function. So I need to write my own main program. So let me do that. Let me make a main.c. And I will include Standardio, and I'll make a main program. And let me see what pick is doing. So integer I equals pick 2. And now I'm just going to write some test cases. All right, you see what I'm doing here? Basically, I'm exercising my pick function. Sorry?
Some sick van commands.
Yeah, that too. So I'm exercising my pick function, right? And I believe, pick of 2 should give me 2, pick of 3 should give me 3, pick of -1, I'm not going to do -1 because I don't know what that should do. Let me do pick of 11. And that should give me, 3, the remainder when I divide by 4. And pick of 4 would normally be 0, but it should give me 1 because we're not allowed to give 0. And pick of 5 should give me 1. I'm going to do this. I'm going to compile main.c and pick.c and turn that into an executable program main. And now if I run this, I can see that, you know, my code's not doing the right thing. It's you know, doing something weird. Alright, so I'm going to edit my pick program and hopefully make it do the right thing. And I'm going to recompile my test bed and I'm going to run main. And now it looks like it's working, right? So I fixed my problems in pick.c. So it's giving me this number modulo 4, except when this is a multiple of 4, in which case it gives me 1. So now I think my pick.c function is good, right? I didn't show you the changes I made to it, obviously. So now I'm going to go ahead and rebuild my test bed. And I'm going to go ahead and reassess. And upgrade, and there's your 10 out of 10, so you're good to go.
What was that not command?
The what? Oh,
You
this?
just did not assess.
So if you do history, it will show you the last, you know, 5,000 commands that you've executed. If you say exclamation mark something, it will pull back the last command that starts with that. It's potentially a little dangerous, but like if I want to recompile, I can just do exclamation GCC, and it'll pull back the last GCC command. But it can be a little goofy, because if you have some command with R you want to recall, but you actually did an rm-rf star recently, you can inadvertently execute that. So, buyer beware.
Question.
Yeah.
So just to recap that line of code where you're compiling, so you're compiling, so you're telling it to put the executable code into the Makefile, but you're telling it after that to take the pick.c and put it into the main function. In this case, it's one that you have, but if we wanted to do our own main function, we have to put the main.c, and the second argument, it knows to execute it into that second argument.
Yeah, you got it. So this is this business that when you say GCC, there's a bunch of things that happen. There's compilation, but there's also linking. And so if I compile, you know, and I name two C programs, those both get compiled and then linked together. But since this program is not a .c, it's a .o, it's already been compiled. So it's going to compile this C program, and then it'll link that to this already compiled C program, and that gives you your executable program when we put that in pick.
Okay, that makes sense. I guess it's, so you just have to remember to do pick.c first.
You could do these in either order.
Okay.
You can do that in the opposite order, and that works just as well. The only critical order is when you say -o, make sure you put pick right after that.
Right, okay.
Yeah, GCC is a really smart function. It'll usually figure out what you're after.
So basically it just looks for the function that has the main in it, and then it'll already know that that's the one to put the function into.
Isn't that the linker's job, though?
Yeah, and the linker gets executed by GCC.
Yeah.
There's assembly, and there's compilation, and there's linking.
Fascinating.
Yeah, it's and the linker, if you want to know like what's really going on, dig into the linker. That's always kind of where the heart of it all is. And if I do something like this, if I tried to link in my own main.c here, right, I'd get a message saying there's multiple definitions of main. It's telling me, hey, there was a main program in this .o, but there's also a main program in my .c. You can't write a program that has two mains, right? So when we're linking, we just do that one.
And you could do any number. Obviously, you could do any number of .c files as long as one of them has the main. You're all set.
Yep, you can do multiple .c's. You can do multiple .o's.
What's a .o?
So a .o is an object file. So let's dig into that a little. So when you start off with like a pick.c, you can say gcc-c pick.c and create a pick.o. And then you could have, you know, a main.c and do a gcc-c main.c and turn that into a main.o. And these are objects. They're binary, they're machine readable rather than human readable, but they're not executable. They're basically the sort of pre-digested, compiled versions of your C code, and they're ready to get linked together. And so these could go through a linker to create an executable program. And if I want to link them, I could simply say gcc-o main, and I could list these in whatever order I want.
So
And that'll
link
tie 'em
files,
together.
You always have to turn them into object files first.
No, so yeah, if you want to link them, you have to turn them into objects first. But if you just say gcc-o main pick.c main.c, this is happening internally, but then it gets rid of these .o files, so you don't see them sticking around.
Oh, so you don't actually need it.
Yeah.
Very cool.
Yeah, there's lots of magic under the hood.
Can you just put a folder in that?
Can you do what?
Say you had like 20 files that you wanted to put, and then you had the main file in a directory above it or whatever.
Mm-hmm.
Could you put an entire folder in that and just type in the folder, and then everything inside that folder would get linked in?
You can't name a folder, but you could say, you know, folder/star.o.
You could make a batch script to take everything out of the folder as long as it's a C file and compile that.
Mm-hmm.
The GCC command.
Cool. Yeah, you could use a bash script. And pretty soon, not today, but pretty soon we'll talk about Makefiles. And Makefiles are a way to do exactly the kinds of things that you're coming up with right now. Because this is a common situation where you have a lot of C files, and you know, typically some of them have already been compiled. Maybe one of them you've changed, and so that needs to be recompiled. But if you've got 10,000 C files, you don't want to recompile all 10,000 just because you changed one, you know, 6-line program. So if you know what gets affected by that change you made, you can recompile parts of what's in your folder and then link them together. So Makefile is a way that we can describe to Bash exactly how a project should be made, how an executable should be created. And we write a recipe for that, and then anytime that you make changes to your code, all you got to do is say make, M-A-K-E, hit enter, and it will figure out what needs to be recompiled based on dependencies, based on timestamps, and all sorts of other stuff. And so I debated doing a Makefile for PA2, and I decided not to. But certainly by the 4th programming assignment, we'll be making Makefiles for our C programs. And then in 222, we'll use Makefiles every project. Oh, that's some awesome sunlight.
Multi-threaded stuff.
We'll touch on creating processes a little bit at the end of this course, but not in any kind of disciplined way. We don't really get into like threading until 223 in spring. And we do it in Java, where it's a whole lot friendlier than trying to do it in C.
Another question.
Yeah.
What's with the order of the classes?
Oh, it used to be 222, 23, 24, right? But 224 really kind of like helps build your knowledge of tools that you can use in these other courses, right? It's helpful when you get to 222 data structures. It's helpful if you're really good with GDB, the debugger. It's helpful if you know how to use Makefiles, if you know how to use Git, all of these kinds of things. It seemed that you know, students would, for example, take 121, and then there might be a year before they get to the 200 CS sequence. And if you haven't been writing C code for a year, you're probably pretty rusty on it. So 224 is not just tools and building up your toolkit, but it's also, you know, kind of a refresher on C, and sort of making sure everybody's at the same place. So we decided to move it in front of the other courses several years ago. But to change the numbering is, you know, almost literally an act of Congress. And so we just keep them in a weird order.
So, how do we get how would I get to like the .o file, like produce the .o file? Because normally when I compile it, I pass it the .c's, and then presumably it creates the .o file somewhere.
Mm-hmm. So when you do a gcc-c, that'll make a .o file. So let's just try this. So I can say gcc-c pick.c, and now I've got a pick.o, and that's the compiled version of pick.c. And I could do a few things. I could say gcc-o main.c pick.o, and that'll compile those together. Or I could actually turn my main into a .o. So I have two objects, main.o and pick.o, and I can link those like this, and it gets me to exactly the same place.
Okay, cool.
Yeah.
What is that -c argument up there?
-c says compile it, but don't build an object.
Okay.
So if you do a man space gcc, the G option says not to run the linker. So the output consists of object files output by the assembler. So we do the first few steps. You convert from C to assembly language, and then you assemble from there into an object, and then it stops.
Gotcha.
This is a really cool man page to browse through sometimes when you have time to spare, because it really exposes kind of a lot of architectural information, like all the different warning options, right? You can have checking on array bounds, even though arrays don't have an inherent length. In C, you can have boundaries put in, so that if you go outside an array, you'll get like a stack smashing error or something like that. And tons of debugging options and tons of ways to optimize. And sometimes, you know, optimizing is good, but when you're debugging, optimizing may not be something you want, because the optimizer may, you know, change your code to do something different, have the same effect, but do it in a different way from how you wrote it, and that can make debugging interesting. But, you know, also from GCC we can get to the assembler, we can get to the linker, we can also get to the preprocessor, and the preprocessor is what picks up all of those commands that start with like a number sign, like number sign include, and if you do number sign define, and so on. Those are all processed before your code is compiled. So there's actually an earlier step even before compilation, which is pre-processing. And then the pre-processing is usually a bigger C file, and that goes through an assembler, and then the assembly turns into an object, and then the objects link into an executable if that's where you're heading. All right. Let's dig into functions a little more. Could I have more shadows? just took
You're in
down.
a different spot.
Yeah, I'm in a house. New house.
Did you move or?
Yeah, I moved over the weekend.
Oh, very nice.
So living with my fiance and daughter, and in the process of getting stuff over here and getting stuff set up. Alright, well we'll fake it with shadows now. I'll get a big bright light later. So functions, right? So in your main program, well, let's write some code. So let's make a function that adds two numbers together. So let's say integer I equals add 2 comma 3. Alright, pretty straightforward function. Now I can put the function in this file, or I can put it in a separate file. I'm going to go ahead and put it in a separate file just because. So integer add integer a integer b, and we're going to return a plus b. Alright, so what's going on here? First of all, in my main program, right, when I say add, right, anything that's not a part of the C language, the compiler is going to assume it's a function, right? Printf is not part of C. Printf is a function. It's a function, and I'm passing an argument to it, which is a string, and I'm passing an argument, which is an integer. Now, it's a standard function that you'll always find in any implementation of C, but it's not really a language element. If you look at the syntactical description of C, you won't see printf, right? But you'll see a way to call functions. So this is not, you know, a regular language element, ADD, so it's going to assume this is a function. And we list the arguments to functions in parentheses, and they're separated by commas, and they can be pretty much anything. Now I've just got a pair of numbers here, right, 2 and a 3, and I add those together and I return this value I. So functions can take arguments, and they can also return a value. And so when this line gets executed, what's going to happen? Well, the system is going to find the code for this function add, and it's going to start executing it. And in that function, presumably there's 2 arguments that are specified, and the first argument will be set to 2, the second argument will be set to 3. At some point during that function execution, there should be a return statement. And it should look like, you know, return something. And whatever that value is that's in the return argument, that basically becomes the value of this. And so if I say integer I equals this, I will be set equal to that value that was returned. Right? So it's a general mechanism. You can pass information to a function, you can get information back. And you know, if I said printf I equals %d \n quote comma, and over here I said add 2 comma 3, exactly the same thing happens, right? It calls a function, it passes 2 and 3 as the arguments, and then when it comes back from a return statement, this, you know, if I had that right here, would be replaced with the value that was returned. So that would work exactly the same. Alright, so let's compile this and play around with it. Alright, so let me get rid of my pick functions. So here's an easy way to just compile everything, right? I'll say compile main.c and add.c, and let's put the output into our main program. And there's a main.o sitting around because I had one before, but let me get rid of that so we don't confuse things. Alright, so we'll compile stuff up, and if I run main, it'll say I equals 5. right? Which is what we expected because we said add 2 comma 3.
Question about that file.
Yeah.
If you go to that add.c file, there's, I don't know if that, you do int add, int a, and b,
Mm-hmm.
and you don't have to prototype it at all.
So I think I have my warnings turned off, but let me see. Yeah. All right, let me do that. All right. So normally when you try to compile, right, you'll get a warning like this. I was going to change it to floats to force it, but yeah, so you get a warning. So what is the warning happening here, right? It's saying implicit declaration of function add. In other words, I wrote a main program, I said call this function add. It doesn't know anything about add. It can see I'm passing 2 things that look like integers, and I'm taking the return value and storing it into an integer, so it can guess, this probably takes 2 integers and returns an integer. But that's just a guess, right? Maybe it's supposed to take 2 real numbers, and the values I'm passing happen to be, the real numbers 2 and 3, but maybe I expect it to have doubles. Well, if this is expecting doubles, that's different code that has to be generated to call it. Doubles take, 8 bytes, and ints only take 4. So you really want your main program to understand what this function is expecting and what it's going to get back. This is why we have to include Standardio.H. If we don't, we'll get the same kind of warning about printf. So we do what's called a prototype, which is really just describing what a function is going to look like. And so a function prototype looks like this.
You can also put it into add.c, correct?
If you put it in add.c, it will help add.c. It won't help main.
Well, you can just do it in comment.
And it won't throw an error, right?
I think it will, yeah.
Because I just did it, and I did ODP 410 and or 210 or whatever it was. Anyways, I did it, and I put the prototype in the file I made with pick.c, and it didn't throw any warnings or errors.
I think if you take it out of pick.c, you also won't get any warnings.
Okay.
Because the main program's already compiled. So if I put this in here, right, now before we have to actually use the add function, the compiler's already seen what add looks like. And I don't have to name these variables because it doesn't care what the names are. The names are arbitrary. What it cares about is it takes an int, it takes a second int, it returns an int. Right? And this is not describing the add function. In fact, nothing in here actually has the code for the add function. That's okay. So the house building example is if you're building a kitchen, right? You don't need to have the sink available to you, but you need to know information about the sink. You need to know, how many pipes are connecting to it, where will those pipes go, what's the diameter on them, so that you can do what you need to do in the kitchen to be ready to connect the sink, right? You need to know how big a hole to have in the countertop, things like that. That's basically what a prototype is. And it's saying, yeah, somewhere later on down the road when I'm actually doing my GCC commands, then you'll see the sink, you'll see the add function, right? All you need to know is it's going to take 2 integers and return an int. And as long as it knows that, it should go ahead and compile and link just fine.
So, are you allowed to just say int in the arguments of your prototype and then name them later?
Mm-hmm. Yeah, because the name is totally random.
Right.
But you could put whatever in here, and it's going to basically ignore that.
Right.
Because the names really only come in when you're actually writing the function itself. And in this case, I call them A and B. I could call them aha, and I could call them B. code like that, and that'll work fine too. But the names are you know, only relevant inside this declaration of the add function. So usually we just do them like this. Well, usually what I end up doing is just grab this line, and then I just like paste it and throw a semicolon at the end. So I end up with names in my functions usually, but they don't do anything.
Question.
Yeah.
If you have, say, multiple files with multiple functions in both of them, isn't there a way to do something like an include, where you could name all of the functions used in an include?
Yeah, and let me do that with a warning. So if you had a bunch of functions, right, you have an add function and a subtract and a multiply and all this, you would end up putting these prototypes, you know, you'd have a bunch of things in your prototype, and if you had multiple functions that were going to use those, you would end up writing these lines a bunch of times. And so this is where we can make an include file, make our own .h file and put these prototypes in. Same thing somebody mentioned in the beginning of class structures, right? Where, you know, you might end up declaring this structure in multiple files. We can put structures into an include file also. But I don't want to go through that in too much detail yet, because you never want to put like executable code in a function. And inevitably, if I start talking too much about includes, what I'm going to see is people putting this code into a .h and including it, and we really don't want to do that, because that's going to circumvent a lot of what we try to do with Makefiles. So yeah, if you're already familiar with includes, that's exactly where we would use them, is to put in those prototypes.
And limit compile times down.
Yeah, yeah. And well, I don't know if that really saves your compile time.
Not when the programs are this small.
Well, compile is for things smart.
Yeah, yeah. But it's mostly a convenience of not having to type in all of those prototypes, and then when you add a new function, having to go through every program and add an extra prototype to each file and so on and so forth.
I don't know if it was just the flavor of C and C++ I was using, but when I programmed for Unreal, it would, you generally never put stuff in the header file, because then your compile time is another 12 seconds longer.
Yeah.
You work for Unreal?
Yes. Well, I didn't work for Unreal, I programmed in Unreal.
Okay.
Yeah, I was just
But once you rebuild shaders a few times, you like give up all hope of fast anything.
Exactly.
So Standardio H, right, is among other things, it's a bunch of function prototypes. So you know, here's the prototype for fprintf. The thing that it returns, the type of arguments that it expects, and so on. Here's the prototype for printf, and so on. All right. So what else should we know about functions in our last 50 seconds here? Send me an attendance note. Let me know you're here at the end. If you do something like, you know, try to call add with more arguments than your prototype says, you'll get a fairly reasonable message: too many arguments for function add, right? And it'll tell you, hey, here's where you tried to call it, there's your 3 arguments, here's where you declared it, and you said it had 2 arguments. So error messages from GCC are generally pretty useful. They may have a lot of other stuff in them, but usually somewhere in the output you'll find, you know, information that will actually help you figure out what the error is. And usually you want to find the first error message and go with that one. And so same thing, if you have too few arguments, right, it'll say too few arguments, you call it with one argument, but you declared it to take two. And same thing if you have the wrong type, it may or may not tell you about that. But then all bets are off. All right, so we'll dig more into functions tomorrow, and then I want to start looking at dealing with strings and passing char stars and arrays to functions, and that will get you pretty much in good enough shape to use functions fluently for your stick program, if you want to go that route. And so we'll talk about modularizing stick into functions tomorrow also. All right, have a good one. I'll see you in 2:15, or I'll see you tomorrow.
Have a good day.
Thanks, have a good one.
You bet.
You too.
I have a question.
Well,